Okay, hey everybody. This is the second video about sound. So here is what you need to have to start this video. Please have your science textbook open to page 220 and have your science activity manual open to page 146. So textbook, page 220, activity manual, page 146. You should also have a highlighter because we will be highlighting terms just like we do in school to help you to understand and remember the important things we're learning. Okay, I'm going to go to our PowerPoint and we're going to have a brief review from yesterday. First of all, every sound starts because something moves. Rapid back and forth movement is called a vibration. Sound is vibration that can be heard. A disturbance that moves energy from place to place is called a wave. And yesterday we talked about the fact that a slinky is a great way to demonstrate what a sound wave looks like. We talked about the parts of a sound wave yesterday. When the particles are close together, it is called a compression. When the particles are further apart, it is called a rarefaction. So we talked about that yesterday, and you took some notes, and these are the notes we took yesterday. I'm just going to go through those. Okay. Today, we're going to start at the top of page 220. So please look at the top of page 220 in your book. Frequency and speed. Sound waves cannot be seen, but they can be measured. The distance from one compression to the next is called a wavelength. So, when you look at the screen, you see from one compression to the next is called a wavelength, and it is marked there on the PowerPoint for you as well. Please highlight that in your book. The distance from one compression to the next is called a wavelength. Different sound waves have different wavelengths. These lengths are determined by how quickly the source of the sound vibrates. Sounds that vibrate quickly have short wavelengths. In your book there, you will see a picture of a wavelength, just like I have up here on the screen. Next paragraph. Machines and tools have been developed to help us see pictures of sound waves. That "see" is in parentheses because you're not really seeing the wave. An oscilloscope uses a type of microphone to convert mechanical sound waves into electrical impulses. Then the electrical impulses are shown as a wavy line on a graph. So this is a way to see, quotes, a sound wave. So it's changed into an electrical impulse. This is an oscilloscope, and it shows you the wave after it has been changed into an electrical impulse. I would like you to highlight the sentence with oscilloscope in it. Oscilloscope is italicized. An oscilloscope uses a type of microphone to convert mechanical sound waves into electrical impulses. You're going to highlight that in your book. Then you're going to look at the top of the next page, the next column. The number of sound waves per second produced by a vibration can vary. As the number of waves changes, so does the frequency of the sound. Frequency is the number of waves that pass a point in 1 second. And frequency is measured in a unit called hertz. So you're going to highlight those two sentences. Frequency is the number of waves that pass a point in 1 second. Frequency is measured in a unit called hertz. Up here on the screen, this is a high frequency wave, so many waves will pass in a second. A low frequency wave, fewer waves will pass in a second. And the measurement for these waves is hertz, and it can be abbreviated as Hz. That is how it is measured. I'm going to show you a short video now. And it's just going to give you a little bit of information about frequency, just to see if you can get a better picture of what they're talking about.
Sound waves generally have four main qualities: a frequency, which determines the pitch of the note, a wave shape, which determines the timbre, an amplitude, which determines the volume, and a phase, which determines how sound waves interact. We will spend the next couple of videos discussing these qualities. If a string vibrates back and forth 200 times a second, it's causing or emitting 200 sound waves per second. And the number of sound waves that pass a fixed point per second, or the number of times a string vibrates per second, is called the frequency and is measured in hertz. So our string is vibrating at 200 hertz. When you play middle C on a piano, the frequency is 262 hertz. This means the string, and therefore the air, is vibrating back and forth 262 times per second. When you play middle A above middle C on a piano, the frequency is 440 hertz. Again, this means the string is vibrating back and forth 440 times per second.
Okay, I just want to show you that brief clip just to give you a better idea. So, when you play the note on the piano, middle C, 262 hertz or Hz, that means that sound, that vibration is 262 times moving back and forth in a second. So that is frequency. The number of waves that pass a point in 1 second, the number of vibrations in a second, which creates sound. And remember, some sounds have high frequency, some sounds have low frequency. Look at the next paragraph in your book. We're in the second column, second paragraph. Sound waves travel in all directions away from the source of the sound. A sound wave can also travel through different types of matter. The siren of an ambulance can be heard, whether you're in a house, in a tree, or underwater in a pool. Sound waves move at different speeds in different types of matter, though. The density, or how close the matter molecules are, affects how quickly the vibrations move from one particle to the next. The density of the matter also affects how far the sound waves can travel. Sound needs particles in order to move. Remember, it is a mechanical wave. Mechanical waves can only move if there are particles of matter there for it to move through. Of the three states of matter, gas is the least dense, so sound moves the slowest through gases. The sound energy cannot easily move from particle to particle. Also, some of the energy gets used up as it travels through the space between the particles. That slows down the movement of the wave. Air is the most common type of matter through which we hear sounds. The speed of sound in air is about 335 meters, 1,100 feet per second. So you're going to highlight that, and I have it up here on the screen. Speed of sound through the air, the most common way we hear sound. This is how fast sound travels through, now we're on to page 221, travels through the air under specific atmospheric conditions. In different conditions, such as hotter day, the speed of sound will be different. That's why we have the word approximately, which means give or take a little. So depending on the weather that day, sound might travel a little bit faster than that or a little bit slower than that. The particles in liquids are denser than the particles in gases, so sound moves more quickly through liquids than it can through gases. The waves also travel farther than they can in a gas. Solids are the densest state of matter. Their particles are very close together. The sound waves easily move from one particle to the next. So sound waves can also travel faster and farther in a solid than in a liquid or a gas. All right. So this little graph is in your book as well. It shows you sound travels through the air 335 meters per second. Water, 1,500 meters per second. Oak, like an oak tree trunk, 3,900 meters per second. Iron, 5,955 meters per second. So one thing we can do by looking at this chart is understand that sound travels fastest through solids, slowest through air. Now, in order to explain that better, I have some more examples on this PowerPoint. So, sound travels fastest through solids because it needs particles in order to move, and the particles in the solids are the most densely packed together. If you remember way back in the middle of the year, maybe it was November or December, we talked about what the molecules of a solid, liquid, and gas look like. And we learned that the solid has molecules closely packed together. They are moving little tiny bit of vibration, but they're densely packed. Sound needs particles to pass through. So the closer the particles are together, the faster the sound gets through them. So sound travels fastest through solids. Then we have sound travels more quickly through liquids than it does through gases because the particles in liquid are more dense. So here's the particles in a liquid. Hopefully you remember this from earlier this year too. So they're not as close together as the solid. There's a little bit of space between them, but they're still pretty dense. So sound travels through them pretty quickly. Then we get to gas. Sound travels slowest through air, through gas, because the particles are spread far apart. And you can see in a gas, the particles are very far apart. So it takes the sound longer because it has to travel through the air, hit the particle, travel through the air again. So you need to know that sound travels the fastest through solids and the slowest through gases. Look at the last paragraph on page 221, second column. The speed of sound is not the same as the frequency of sound vibrations. Speed tells you how fast something is moving. Think of watching cars traveling on a straight highway. Suppose all the cars on this highway are traveling at 50 kilometers per hour. That is the speed of the cars. However, the frequency of the cars is the number of cars that pass you in a set period of time. Frequency is how often they pass. In the first minute, perhaps only one car passes. In the second minute, 5 cars may pass. The speed of the cars will stay the same, but the frequency changed. The speed and frequency of sound waves are related in much the same way as the speed and frequency of the cars on a highway are related. Okay, the next thing I'm going to do is show you another video, and honestly, this is one of my favorite videos for explaining sound. I've never seen another video that does a better job of explaining this concept. It is excellent. Make sure you are following along.
Transmission of sound. Every sound is produced by a vibration. Vibration is the back and forth movement of an object. As you speak, vibrations are produced by the vocal cords in the throat.
In your throat.
You can hear only when the sound energy reaches your ears. But how does sound energy travel? Wonder how that works? Come, let's go across to Dr. Zook. Sound energy travels in the form of sound waves. There are mainly 2 types of waves, transverse wave and longitudinal wave. Let us see how waves travel. We can use a slinky spring to observe both types of waves. Emily is holding one.
Okay, the first type of wave they're going to demonstrate is a transverse wave. That is not the kind of wave that we are learning about right now. That is the wave that goes up and down and up and down. Those are actually light waves, and they will be taught about in chapter 10. It's part of the video, so we're going to watch it. I just don't want you to get confused. The transverse wave is not the sound wave. The longitudinal wave, the second example, will be the sound wave.
Side of the slinky, while Dr. Zook is holding the other end. With a quick upward flick of the wrist, Dr. Zook has sent energy traveling through the slinky. Notice how the slinky moves? This is a transverse wave. In a transverse wave, the particles vibrate at a right angle to the direction of the wave. The wave traveled from Dr. Zook to Emily and back. Now let's see what a longitudinal wave looks like. Emily is holding one end of the slinky,
the sound wave
while
right
Dr.
here.
Zook is pulling its other end towards himself and then pushing it towards Emily. Watch closely, and you will notice that some of the coils crowd close together and then slowly move farther apart. This is because the vibrations are parallel to the direction of the wave. If the wave moves from right to left, then the particles also vibrate from right to left. This is a longitudinal wave. Sound waves are longitudinal waves. These waves travel at different speeds in different mediums. The medium could be a solid, liquid, or gas. Now let's see how this works. In a solid, the particles are very close together. Sound energy moves as one particle hits the other particle. With the particles being so close together, sound travels quickest through a solid. If we look at particles in a liquid, they appear to be slightly further apart when compared to solid. Thus, sound energy takes a little longer to travel through a liquid. Look at the particles of gas. They are spread out, and hence, sound waves travel most slowly through them. Now we know how sound travels in different media. The vibration of particles produces waves. Wavelength is the distance between two consecutive compressions or rarefactions. The number of waves passing through a point in a second is called frequency, and it is measured in hertz. Sound waves travel in all directions.
Emily?
Sound gets reflected. That is, it bounces back on hitting a solid surface. Bouncing back of sound is called echo. Bouncing back of sound is purposefully used in detecting depth of seabeds. That's amazing, isn't it? Summary: every sound is produced by a vibration. Vibrations are produced by our vocal cords when we speak. There are two types of waves, transverse wave and longitudinal wave. In a transverse wave, the particles vibrate at a right angle to the direction of the wave. In a longitudinal wave, vibrations are parallel to the direction of the wave. Sound waves are longitudinal waves. Sound travels quickest through a solid. Wavelength is the distance between two consecutive compressions or rarefactions. The number of waves passing through a point in a second is called frequency, and it is measured in hertz.
Okay, like I said, that is my absolute favorite video for showing you the sound waves and how sound travels fastest through solids, then liquids, and slowest through gases. I love the pictures. I love the illustrations to show you. So hopefully after watching that video, you really are understanding this better. Now, look at Activity Manual, page 146. And like I told you yesterday, I don't have a copy of this with all the answer key in it. That is at school in my podium. You guys know my blue podium, so I don't have it. So I'm going to put the answers up on the screen and you're going to write them in. The first one we're going to write is wavelength. That is the purple box next to wave. Okay. You're going to write in wavelength, the distance from one compression to the next. Okay, the next one we're going to write in is speed. At the very top, it's orange, and it's the only little square at the top. Approximately 335 meters, or 1,110 feet per second through the air. Approximately because depending on temperature, humidity, it can be a little slower than that or a little faster than that. That's why we use the word approximately. Okay, so go ahead and finish writing that in. All right, then the third one you're going to write in is frequency. The number of waves that pass a point in a second, or the number of vibrations in a second, like we saw in the video. The number of waves that pass a point in a second. Okay, now a couple questions. What is sound? We talked about this on the video yesterday. The basic definition of sound is a vibration that you can hear. Sound is vibration. What is a wavelength? It is the distance from one compression to the next on a wave. And I've given you lots of examples of that in the PowerPoint. Through which type of matter can sound travel faster? A gas or a solid? Well, hopefully after this video today, you can tell me that a gas can travel more quickly through a solid because the particles are densely packed together. All right, so your assignment today is this. You are going to complete Activity Manual, pages 147 and 148. You will see at the top of 147, it says Study Guide, so you know what that means. You're going to fill in each blank. And then on page 148, it says, for numbers 12 through 20, write T if the statement is true. If the statement is false, write the correct word that would replace the underlined word. So you're not just going to write false. And then there's two questions at the end, 21 and 22. And those questions have to do with the difference between frequency and speed, which I read about a moment ago. So speed, easy. You know what speed is, how fast something goes. So let's say we're on 97. That's a road I take every day when I go to work in Bowie. So the speed limit on 97 is 65 miles per hour. So the speed of the cars going down 97 is 65 miles per hour. Now, sometimes it's faster than that because people speed and break the speed limit. But let's assume that everybody is obeying the law today and they're all going 65 miles per hour. That is the speed. Now, frequency is how many cars pass a certain point in a second. So if I'm standing on the grass or in the trees next to 97, and I am counting and I'm calculating frequency, I'm going to count how many cars are going past that point where I am in a second. If it's the middle of the night, there might only be 1 or 2 cars that go by in a second, maybe none. If it's a rush hour, it might be 8, 9, 10, 15, depending how many people are going by. So frequency is going to change. The car speed didn't change, but frequency is how many pass by a certain point in a second. Okay, so that's the difference. And those two story problems at the end, that's what they're talking about, the difference between frequency and speed. So you can either write the answers in the study guide first and then put them in LMS, or you can go right to LMS and put the answers in, whichever way you find easier. And that is all for today, and I will see you next time for more about sound.